Hello dear students, let me begin the first chapter of this course. In the first lecture, we will understand the definition of the line integral of scalar fields, and then we will learn the definition of the line integral of vector fields, and we will also understand the geometrical interpretation of the line integral. This lecture is gonna be very important, and we will also recall some of the basic concepts from the calculus. So let me start the discussion. A line integral is basically a generalization of the single or definite integral. The definite integral is also called a single integral, okay? So it means that a definite integral is basically a special case of the line integral. We also know from basic calculus that in an ordinary single integral or definite integral, which is this one, this is the definite integral of the function f with respect to x on a closed interval from a to b, which lies on x-axis. And this definite integral f is defined and continuous on the closed interval from a to b of x-axis. Okay, now we will recall the geometrical interpretation of the definite integral, this one. Okay, for this, consider the graph of the function y equal to f of x from a to b. Okay, this vertical line is the line x equal to a, and this one is the line x equal to b, and this is a region which is bounded by these two lines x equal to a, x equal to b, and the x-axis, and the graph of the function y equal to f of x. These four things are bounding this region, and the area of this region is basically the definite integral of the function f with respect to x from a to b. Okay, so this was the geometrical interpretation of the definite integral of f from a to b. So hopefully you have recalled it clearly. Now we will move forward. In the case of a line integral, the function f is defined and continuous on a curve C lying in a domain D of xy plane. So this is the first difference between a line integral and a definite integral, and this difference is, for the case of a line integral, the underlying function f, which is the integrand, is defined and continuous on the curve C in some domain D of xy plane. Okay, on the other hand, for the case of the definite integral, the function f is defined and continuous on some interval a to b of x-axis, and note that this interval would be a straight line lying on the x-axis. So we know that a straight line is a special case of a curve. So from this it also follows that the definite integral is a special case of line integral, or line integral is a generalization of the definite integral. Okay, so hopefully this is clear to you. Now we will move forward. Let C be parametrically described by the vector equation r of t equal to x of t I unit vector plus y of t j unit vector plus z of t k unit vector, where the parameter t varies from a to b. Okay, so we have used the parametric equation of the curve C, and this will be required to define the line integral of the scalar field f. Now we will move forward and recall from the basic calculus the definition of the arc length of some curve C, which you may have also learned in the differential geometry. This definition is s of t, which is called the arc length function, and this is equal to the definite integral from a to t with respect to u of the magnitude of r prime of u, where r prime of u is the derivative of the parametric representation r of the curve C with respect to u. Okay, and actually this formula, which is the arc length function, gives us the length of the portion of the curve starting from the initial point. Okay, we know that the initial point of the curve C corresponds to the point t equal to a. Okay, and in order to understand this formula further, we will consider the curve C, which is suppose this one, and it is traced in this direction, which is also called the positive sense of this curve. The initial point is where t is equal to a, and the final point on the curve corresponds to t equal to b, okay, where t is the parameter for the parametric representation, and this is the curve C, which is parametrically described by r of t, where t varies from a to b. Okay, now if we take some point in the curve and suppose that this point corresponds to t equal to c, then what will be s of c? S of c is equal to the definite integral from a to c. The integrand remains as it is. Now this s of c is actually the length of this portion of the curve, which starts from the initial point and ends at a point where t is equal to c. Okay, similarly if we take t is equal to b, then what will be s of b? This is the definite integral from a to b of the magnitude of r prime of u. Now this s of b is the total length of the curve C. So hopefully the notion of arc length is now more clear to you by this explanation. Now we will move forward and we will differentiate both sides of the previous equation with respect to t. We have this, okay, in which we have just taken the derivative with respect to t on both sides of the preceding equation. Now on the right hand side we will apply the fundamental theorem of calculus, okay. By using this theorem we get ds by dt equal to r prime of t magnitude, where we have applied the fundamental theorem, and from this equation we get ds equal to the magnitude of r prime of t dt, where I have used the definition or the chain rule, ds by dt times dt, this is just equal to the differential of s. Okay, now I will explain you the statement of the fundamental theorem of the calculus, and we will see that how this derivative of the integral is just equal to the magnitude of r prime of t. And for this I will remove all of the pen inks. According to the fundamental theorem of calculus, let f be a non-negative and continuous function on the closed interval from a to b, that is, a is less than or equal to x less than or equal to b. Then the derivative d by dx applied on the definite integral from a to x of f of u with respect to u, this is just equal to f of x. Okay, what is happening here? Although first note that the variable u is a dummy variable, because we know that from basic calculus the variable of integration is always a dummy variable. Okay, so u is a dummy variable, and here the derivative cuts the integral, and the dummy variable u is replaced with the upper limit of integration, which is the variable x. Okay, so therefore the derivative of this integral is equal to just f of x. So it means that by using the fundamental theorem of calculus, the derivative with respect to t of the integral from a to t of r prime of u magnitude du, according to this definition, the derivative cuts the integral, and we have the integrand, which is the magnitude of r prime of u, and the dummy variable u will be replaced with the upper limit of integration, which is the parameter t. So this is equal to the magnitude of r prime of t, and this is what that I have used at this point. So hopefully this is now clear to you. Furthermore, the ds is also called the arc length element. Okay, we will use it in the definition of the line integral of scalar field. So let me move forward. Now we will discuss the smooth curves. The smooth curves are very important to consider because the line integrals that we will solve throughout this course would be along the smooth curves or piecewise smooth curves. But before defining the smooth curves, we will first define the tangent vector. The tangent vector to the curve C is given by the derivative dr by dt, that is the derivative of the parametric representation of the curve C with respect to the parameter t. Okay, and this is what that you may also have learned in the basic calculus or in the basic differential geometry of curves. Okay, now we will define the smooth curve. We call a curve C a smooth curve if there is a unique tangent at every point of C whose direction varies continuously as we move along the curve C. Okay, for example, the curve this one. Suppose that this curve is traced in this direction, that is in the direction from left to right, which is its positive sense. The initial point is, suppose this be the point A, and the terminal point B, the point B. Now, as we move along this curve from point A up to the point B, then clearly the tangent vector varies its direction in continuous fashion. Furthermore, there is no point in this curve at which there are two or more tangents. So therefore, the tangent vector is defined in unique way at every point of the curve C. So according to this definition, this curve is a smooth curve. Okay, now consider another curve, this one. Suppose this point B the point A, which is the initial point, and suppose this curve is traced in this direction, which is also from left to right. Suppose this point is the point B and the terminal point of the curve is the point C. Okay, clearly this curve ABC consists of two curves that are joined end to end. The first curve is the curve AB, this one, and let me call it the curve C1. And the second curve is the curve BC, and suppose this is the curve C2. Okay, now the point P, which is the corner point. At this point we have two tangents. The first tangent is this one, which is the tangent to the curve C1 at the point B, and we can also define another tangent to the same point B, which is this one, and this is the tangent vector to the curve C2 at the point B. So it means that the tangent vector is not uniquely defined for this curve. Furthermore, the tangent vector varies its direction suddenly. Okay, as we move from point A up to B, then the tangent vector will definitely change its direction in continuous sense. Okay, but as long as we reach the point B and we cross the point B, it suddenly changes its direction. So the direction of the tangent vector for this curve ABC is not varying in the continuous fashion. So this curve is not a smooth curve. However, this is a piecewise smooth curve. Okay, because there are two smooth pieces that are joined end to end to make this curve. Okay, now let me consider some of the examples. A circle is a smooth curve and it is closed. An ellipse is also a smooth curve, and a parabola is smooth curve, etc. On the other hand, a triangle, a square, rectangle, etc. These are the piecewise smooth curves. Okay. From now on, we will suppose that the curve C is a smooth or piecewise smooth curve because the line integrals are always defined and evaluated along the smooth curves or piecewise smooth curves. And in the upcoming lectures, we will learn that how to calculate the line integrals along the piecewise smooth curves. Furthermore, we will suppose that the derivative dr by dt does not vanish on the interval from a to b. It means that there is no point in the curve C at which the tangent vector is the null vector. Okay, this means from the differential geometry that there is no singular point in the interval from a to b. So in defining the line integral, we must suppose that the underlying curve along which we are taking the line integral must be such that there is no singular point in that curve. Similarly, when we will define the surface integral, we will suppose that there is no point in the surface at which the normal vector goes 0 or the null vector. Okay, and these are the things that we will learn in the upcoming chapters. So now we are in position to define the line integral of a scalar field. The line integral of a scalar field f over the curve C is denoted by this integral. Okay, we write C in the subscript of the integral, and the integrand is f, and we integrate f with respect to the arc length function s. Here ds is the arc length element, and we know that ds defined as r prime of t magnitude times dt. By using this expression of ds, we can define the line integral as the line integral of f over the curve C equal to the definite integral of f, in which f is written in terms of t, that is, x is the function of the parameter t, y is the function of parameter t. So f will be written not in terms of x and y, but in terms of the parameter t. Okay, and then ds will be replaced with the magnitude of r prime of t times dt. Okay, and then we have the variation of t from the parametric representation of the curve. This variation is from a to b. So the lower limit of integration with respect to t is a, and the upper limit of integration is b. So therefore, in this integral, a is the lower limit and b is the upper limit of integration. So this is how the line integral of a scalar field is defined. And furthermore, note that from basic calculus, you may know that the integrand must be continuous on the interval from which the variable of integration takes its values. So it means that we must assume that f belongs to the vector space C closed interval from a to b. This C from a to b is actually a vector space that consists of all of the functions that are continuous on the closed interval from a to b. Okay, so we are assuming that the integrand f, which is in terms of t, is continuous on the closed interval from a to b. Now we will move forward and define the line integral of a vector field. Suppose that we have a vector field f of x and y equal to p of x and y I unit vector plus q of x and y j unit vector plus r of x and y k unit vector. Here p, q and r are the components of the vector field f. P is the x component, q is the y component, and r is the z component of f. And we are supposing that this vector field is continuous on a domain D. Then in this case, the line integral of f over a smooth or piecewise smooth curve C is denoted by the line integral over the curve C, and here the integrand is f dot dr. Here this dot is actually the dot product of f with the differential of the parametric representation of the curve C, and this line integral is defined to be equal to the definite integral from a to b, in which f is written in terms of t, that is x and y are no more the independent variables, they are the dependent variables and they are depending on the parameter t. So in this way, by writing x and y in terms of t, we can write f in terms of t, and then dr will be replaced with r prime of t times dt, because you know that the differential of r can be written as the derivative of r with respect to t times the differential of t. So by using this definition, we have this thing. So this is one way to define and evaluate the line integral of a vector field. We can find another definition, for which note that the parametric representation is r or r of t equal to x of t. I'm not writing the dependence of x on t, I unit vector plus y j unit vector and plus z k unit vector. Now take the differential on both sides, we get dr equal to dx I unit vector plus dy j unit vector plus dz k unit vector. The components of f are p, q and r, and the components of dr are dx, dy and dz. Take the dot product of f with dr, we get another definition of the line integral of f over the curve C, which has the integrand p times dx plus q times dy plus r times dz. Okay, and in this definition we can take either x or y or z, any one of them, as a parameter, and then we integrate this integral with respect to that parameter. Okay, and we will do this in one of our examples that we will solve in our upcoming lectures. Okay, furthermore, by writing dx as dx equal to dx by dt times dt, that is x prime of t times dt, and similarly dy equal to y prime of t dt and dz equal to z prime of t dt, we get this. Okay, that is the definite integral with respect to t from a to b, and the integrand is p times x prime of t plus q times y prime of t plus r times z prime of t times dt. Okay, so this is another definition that we use to calculate the line integral of the vector field. Okay, so this is how we can define the line integral of a vector field. Now we will move forward and we will consider the geometrical interpretation of the line integral of a scalar field, which is very important to consider. The line integral of a scalar field f over a curve C geometrically describes the area of a fence whose base is the curve C, and the height at any point xy is defined as the functional value of the point xy, that is the image of the point xy under the function f. So this is the geometrical meaning of the line integral of a scalar field f over the curve C. Now we can further understand this concept, and for this I will consider the surface, which is described by the equation z equal to f of x and y, and here f is defined on some certain domain D lying in the xy plane. And we will learn in the next chapter that the double integral of the function f over the domain D is equal to the vertical volume bounded between the domain D and the surface. Okay, And since this is the matter of the next chapter, so we will discuss it in more details in the next chapter. Okay, so let me leave it for now. Now we will move forward and we will take a curve C in the domain D. Okay, and since the image of the domain under the function f is definitely this surface, so it means that the image of the points of the domain is definitely are the points which lie in this surface. So it means that the image of this curve is definitely a curve lying in the surface, which is this one. Let me make it bold so that it will be more visible for you. This is the image of the curve under the function f. Now I can take a point, for example this one on the curve, and suppose this point be xy. Then in this case, what is the image of this point under the function f? For this we have to go straight above this point vertically up to the surface, which is a point on this curve. This point is f of xy. Now I will remove the surface and the domain so that I'm left with this, and we will consider a fence whose base is the curve C and whose height at any point x and y is given by f of x and y, and this fence is definitely this one. Okay, look out at its base. Its base is the curve C, and the height at any point xy of this fence is definitely given by f of x and y, as it is clear from this figure. And finally, the area of this fence is actually equal to the line integral of f over the curve C, and this is the geometrical interpretation of the line integral of a scalar field. So hopefully you have now understood this. This completes our today's discussion. In the next lecture we will learn how we can solve the line integral of a scalar field. Okay, and then we will learn how to evaluate the line integrals of vector fields. Thanks for watching.